Thank you so much for having me here. I know we're all going to be saying this today, but this is my first in-person conference for a couple of years, so it is really exciting to be here. For my talk, I'm going to be sharing some of my experiences as a software developer through the lens of what I've seen in terms of that sort of changing developer experience for devs building AI apps. I joined IBM as a software developer at our Hursley Park site in August 2003, and this is the oldest photo I could find of my first desk back in, I think it was November 2003, when you needed a really huge desk to make space for ridiculous monitors. I should say this is a personal talk, so I've avoided using stock photos. All but a couple of the images in my slides are photos I took or screenshots I took of things that I did or worked on, which is why the photos are all going to be really bad. But anyway, so this is where I started, a bit over 18 years ago. I'm still a Batman fan. I don't think I still have the poster. And the other side of this being a personal talk is, keep in mind this is just an anecdote. This is one perspective. This isn't a researched industry history. So I'm sure some of you will have slightly different experiences from me. I have mad snowman building skills, but my excuse for this slide is to talk about AI winters. And you've probably heard of this term before, this idea that in the history of AI, there have been some times when enthusiasm for AI has kind of waned. Now, when did that happen? It sort of depends on who you ask. If you search for AI winter timelines, you can find loads of opinions about what the level of interest was when I joined the industry in the early 2000s. I'm going to leave this debate to historians, but my experience was the business world did seem kind of skeptical of AI. I remember talking to customers where we would avoid using terms like AI because that didn't sound serious. It didn't sound like the stuff of grown-up business. For a lot of people outside tech, AI meant robots and sci-fi, and this is my 3D printed Raspberry Pi robot from my kitchen. He's maybe not the best illustration of sci-fi AI robotics, but I thought he was cute. We were doing projects that I think we would describe today as AI. I did quite a few natural language processing projects, but we rarely called them AI. We'd call it analytics or data science or big data. Business was really excited about big data. Those sounded grown up. Those sounded like serious things that businesses should invest in. AI didn't. But the work was still happening. AI tech back then needed a lot of hardware. A project often involved some sort of server build. And these photos are from early on in one of my projects, the day the hardware arrived. It was like Geek Christmas. I had loads of boxes to open. In the top right, you can sort of see the memory modules, I think. That's a blade that we'd unpacked on the desk, the cabinets at the bottom there that we'd built into. This was a fun day. And again, excuse the terrible photography skills. I didn't think that, 15 years later I'd be using it in a slide. I got seriously picky about cabling. My builds would always start out really tidy. They didn't always stay tidy, but they started out tidy. Now, don't get me wrong. Not every project involved shiny new hardware. I think this one had some sort of security requirements that it needed shiny out-the-box hardware. More often, projects would start by scavenging from previously completed projects to assemble some sort of Frankenstein cluster. Because back then, we didn't have cloud resource. We didn't have computers sat around ready for use. We weren't at the point where compute resource was this elastic thing where we could just use what we needed on demand. And AI projects needed a lot of tin thrown at them. Resource requirements was a huge factor in every project. Now, keep in mind, when I say resource requirements, this is all relative, right? Now, you probably heard about the project IBM demoed in 2011, an AI system playing a TV quiz show. Now, this is the slide where I've had to resort to stock photos, because I didn't work on this project. The TV quiz show was February 2011, and I joined the team, the Watson team, in April 2011, like a couple of months later. When I joined, Watson was physically huge. It was 10 racks holding 90 servers, nearly 3,000 processor cores. And what did that monstrous amount of hardware get us? The ability to understand and answer one question at a time from one questioner. It looked for answers in this corpus of general knowledge text sources, encyclopedias, dictionaries, newspapers, magazines, that sort of thing. And that sounds impressive, right? Watson could look for answers in all of Encarta. But how big do you really think that is? Because we were just using the text, we weren't using images, and text doesn't take up all that much space. Encarta was 0.3 gigs. All of the back issues of Time magazine, couple of gigs. The whole seed corpus for that original quiz show project was 70 gigs, 70 gigabytes. I mean, that's big, sure, but it would probably fit on your laptop. And we were filling a room with 90 servers to be able to use it. So, projects typically involved a lot of hardware, setting up hardware specifically for your project, and often a lot of hardware. And the other thing is they involved writing a lot of custom code as well. By 2012 to 2014 sort of time, I was mostly working on healthcare projects, and that means I can't really show you data from those projects. But I found some screenshots that I used when I was training new engineers that joined the team, and that was all public domain data, so I'm going to use some of those. Everything revolved around experiments. We'd have sets of test questions, questions that we knew what the right answer was for, and we'd run them through the system and compare the answers we got from the AI system with our right answers. And we'd use the results from each run to come up with a theory for what we could change to make it better. So run the test questions, see how the system performed, change something, and then run the test questions again and see what happened. Did you make it better? Did you make it worse? But how did we know what we should try changing? Well, the job of the developer was to come up with ideas for that from the data we got in the experiments. The first thing I'd want to do is check to see if the system had correctly understood the question. And we'd use visualizations of how the question text was parsed to see if it had recognized, identified the important bits. Now remember, the real projects we were doing were in healthcare, so the actual questions were really technical and very domain specific. So we had to work closely with medical subject matter experts to help us. And if we could see problems in how the question text was parsed, then we might start making some code changes. Alter one of the question annotators. Maybe write a new question annotator that would recognize bits in this particular type of question. And then we'd rerun our experiment and see what difference that made. But maybe it looked like the system did correctly interpret the question. So the next thing I'd look at would be how it turned the interpretation of a question into search queries. I would look through the passage search queries that the system had generated and the document search queries. And if we spotted a problem, then maybe we'd make some changes to the code that were generating queries. You know, maybe write a new query generator that would generate a different type of search query that would have helped with this type of question. And then after a code change, rerun your experiment and see if you'd made things better or worse. Maybe the search queries were good, but the way we were picking answers out of the search results were letting us down. So you would go through each of the candidate answers that were picked out of each of the search results, and you would see if anything was missed. Maybe you'd make a code change there, add a new strategy for picking answers out of search results, and then you'd rerun your experiment and see if it helped. Maybe we were picking good answers out of the search results, but we did a bad job of scoring those answers. Each project had hundreds and hundreds of scorers. Each separate scorer would look at the evidence we found for an answer from a different perspective, and then each of them outputted a score. We'd compare the way that each of the feature scorers would evaluate different answers to understand what was scored highly and what was scored poorly. We'd look at the distribution of scores produced by each of our hundreds and hundreds of scorers. We'd look to see which of the scorers were doing most of the heavy lifting, which ones were always highly scoring the right answers, and which ones weren't really adding anything. We used all of this to help us direct the development of the scorers. It helped us to design and code new scorers. It helped us fix the ones that weren't really helping much. We'd spend so much time looking through experiment results, trying to work out where we should make changes. We'd scrutinize each component, whether it was making a positive or a negative contribution. But obviously, nothing was in isolation. All the fun came from the interactions between the components. Not every change we made would make things better. Sometimes we'd change something and accuracy would go down. And it's not like it was just about the top line. I mean, obviously we cared if a change we made increased the accuracy, but that alone wasn't enough. We'd compare the before and the after in detail, understanding what we'd made better and what we'd made worse. Every change you made, even though it might be small, would have ripple effects that you might not have anticipated. Every code change, it might start as a hunch, but it needed to be verified and justified through the experiments that we ran. We had all sorts of amazing ways of visualizing that, the before and after impact of every code change we made. We'd compare experiment runs side by side to see where we'd improved things and where we'd made it worse. Whether that's the ability to understand questions, or generating search queries, or extracting possible answers from search results, or the evaluation and the scoring of those candidate answers, or the ranking, the weighting of those scores for each of the answers. Hundreds and hundreds of components. This was a huge amount of code. And developing all of this needed a huge team. It's one of the largest development teams I've ever worked on. Experiments took ages to run. And obviously, we didn't have enough clusters for every developer to have their own. So you would have to reserve yourself time on the cluster. In practice, I mean, developers spent so long taking their results away and studying them, let alone turning their hypotheses into code changes, that waiting for the cluster wasn't the tricky bit. But think about what that meant as a developer workflow. From making your code change, at best, you were talking about hours to be able to run an experiment, and then let alone the hours you would take going through all those results to try and understand the impact of what you'd made better and what you'd made worse. I'm not saying all AI projects back then were that huge. Watson was definitely an unusual project, but it had a lot in common with other projects I'd worked on before that. AI projects were often a bit big. They would take months, if not years. They needed a lot of people. They tended to need a huge amount of hardware. Every project was bespoke. Every project was new and unique. Every project needed a lot of code written that was specific to the project, custom annotators, custom feature scorers. And writing that code needed a lot of expertise. And all of that would then need to be redone when you go into your next project. All of this really limited these projects to our bigger customers who could afford and justify this kind of investment. That needed to change. We needed to be able to open this up to more companies. So for us, that meant starting to build out what we called the developer cloud. Companies who signed up to join our developer ecosystem would get their own dedicated cluster that we would host for them. There must be some sort of design pendulum that swings between dark mode and light mode, because when we created this, we were obviously going through a dark mode phase. But it was prettier, right? Because this needed to be usable by people who weren't machine learning experts. This needed to be simple. We weren't letting developers make code changes to this. They could just provide documents for the system to look for answers in, and then training questions to train the annotators and the feature scorers. And on our side, we had to get better at writing general-purpose annotators and scorers that could cope working across different projects. So they would upload their documents into their own dedicated developer cloud cluster, and they would start writing their training questions. They had to write thousands of examples of questions that would train the machine learning system to be able to find the answers to their sorts of questions in their sorts of documents. And then for each question, they had to carefully search for and then painstakingly highlight where the answers could be found in their documents. It would take them months and months of effort. But crucially, this could be done by people who just knew the subject matter. People who are familiar with the questions, knew where to find the answers. And it was in the cloud, technically. I mean, it still needed a huge heavyweight set of servers, and every cluster was dedicated to just one project. But that's sort of cloud, right? It did mean that we couldn't throw the doors open to anyone to play with this. This was available just to companies that had signed up to partner with us, because it needed that large amount of dedicated server infrastructure. And it also took a lot of training. But it was a step forward. From a technology that we could make available for a few customers, we now had something we could make available to dozens. Something that could be trained by developers without a machine learning or AI background who could just fill in forms like this. Something that could be done by a small team. Something that could be done in months, not years. But we needed to get better at moving things to the cloud, making things multi-tenant, making it scale in a way that didn't depend on those dedicated sort of setups for each project. We started with a move to Mesos Marathon. If you want the gory details, I'll put a link to a talk we did for the Linux Foundation. But I stopped needing to care about that. I haven't had to do a cluster build since, about 2012, something like that. And I do miss the early days of having to get stuck in and do hardware builds for each project. But those days have gone. And what this evolution enabled was cloud APIs, proper cloud services, not where a company would have to sign up to be a partner with us and wait for us to provision a dedicated cluster, but something cloud native, scalable, multi-tenant, an API that a developer could start using immediately. The initial trend was towards these small atomic building blocks. This one was our text classifier. You'd give it some text and then train it to be able to put text in the right bucket. So, for example, some email text could be spam or not spam. Some question text could be on this topic or that topic, that sort of thing. Really simple, really lightweight. It needed fewer training examples to get decent results. The system I showed you before needed thousands of training examples to get decent performance. This one needed dozens of examples to get something basically working, and hundreds would get you really good performance. And that meant you didn't need a small team anymore. I saw lots of projects done by single developers. It meant you didn't need months. You could get something working in days. And again, these cloud APIs started meaning developers didn't need to have a machine learning background. So each of the cloud APIs did just one thing. We ended up with about 60 of them at one point. An API for recognizing what language some text is in, an API for translating text from one language to another, an API for identifying the objects mentioned in text, and so on. What that meant for the developer experience was you needed to know how those AI capabilities could be put to use, because text classification isn't a business use case. Sorting through your customer contacts, prioritizing the most angry-sounding customers, that's a use case. Or sorting through questions to recognize commonly asked questions and finding an answer, that's a use case. And those are use cases that a text classifier can help with. But with these small, raw, low-level, atomic sort of cloud APIs, developers needed to build the orchestration for using a combination of these building blocks into their apps. On our side, the deployment continued to evolve. We started using Kubernetes. I couldn't think of a picture to represent Kubernetes, so instead, here is the 14-foot stainless steel bunny sculpture we got in the lobby of our HQ. I don't understand why, but for this talk, I'm going to use the prettiness of the bunny to represent the architectural prettiness of Kubernetes. It sort of works. The next evolution for the cloud services was giving guidance to users who didn't have an AI background. We took what we'd learned from running AI projects and we automated it. We built these orchestrators that could work out what the best thing for the user to do next was, and then prompt them to do it. So, for example, it would start by telling them to upload their documents, their PDFs, their Word docs, their web pages, and so on, and the system would chop them into bits that might be answers to questions. And then it would prompt the user with what they should do next, which is to start providing representative questions, questions that are the kind of things they want to train the system to be able to find answers for. And again, they could just drag those in from a file. Those questions would be analyzed, and the best questions to start training with would automatically be selected for them and put into their next task. We had lots of different ways of picking questions, but the point is, now the system was driving the users. The UI showed a question that the system had selected together with the 4 best answers that it could come up with. The user was asked to rate the answers by just clicking on stars. So instead of where we used to give users thousands of never-ending training questions to create, these were just grouped into bite-sized tasks, just enough questions to make a difference while being doable in one sitting. And instead of making them painstakingly search for and highlight answers, they just clicked on stars to star rate the best answers the system could come up with. If they had multiple users, it would show questions and answers to multiple users and check they were rating consistently. I mean, you always get some sort of discrepancies, but if the number of contradictory ratings went above a threshold that it would start having an impact, then they would get a task to review those conflicting ratings so they can investigate why there's so many differences and do something to fix it. The idea was users didn't need to know to look out for particular AI problems or pitfalls. They would get tasks to prompt them anytime something became an issue. And there were loads of different tasks like this, constantly monitoring how the training was going and working out the best thing they should do next. When it was time for them to train a new model, they'd get a task. Tests would automatically be sorted out for them. They'd just see the summary of the test results. Those test results would also be used to generate their new tasks to work out the best thing they should do next. Now, the workflow was really similar to what I'd been doing 5+ years before, but instead of spending months training developers to be machine learning experts, we were now starting to automate the workflow so it could be followed by people who weren't familiar with the theory. So AI cloud APIs were easier than ever to train. Easier to train because developers were getting more help and guidance to follow an effective training methodology. But also easier to train because as the tech has matured, the number of training examples you need to get decent results has gone down all the time. And still, no custom machine learning code needed for each project. The general purpose scorers and annotators that we've got now were good enough for most use cases. At the same time, the capability of open source tech like TensorFlow has grown exponentially. Projects that would have needed a huge amount of dedicated server infrastructure will now run on your laptop. Projects that would have needed a large team of machine learning experts can now be done by a single novice developer who can follow a tutorial. Projects that would have needed thousands of lines of code can now be done with a few dozen lines of code. So the cloud API started moving away from being those small, atomic, low-level technology building blocks that they were before. We started creating services that brought together interesting combinations of AI technologies, services based on common combinations and patterns of the atomic AI tech. Services that were based on particular use cases instead of being raw, low-level tech. So for example, we've got Watson Assistant that is for creating virtual agents, and that includes a text classifier, but so much more besides. It combines a variety of AI technologies with that guidance to help users who don't have a machine learning background. And the open source frameworks kept getting smaller. TensorFlow, for example, is now available in a JavaScript form that any web developer can now build and run a complex neural network that will run in the browser, no server-side dependencies. And they're simple enough that they can be used by primary school kids, as you heard in the intro, embedded in educational tools like Scratch. And I'm going to be demoing some of these tools at 6:15 in a Tools in Action talk if you'd like to see more. I've overrun my time, so I'm going to leave my summary there. I hope my whistle-stop tour through my experiences has been interesting. I know some of you will have had overlapping or different experiences, so I'll be around for a couple of days. Please come and sort of tell me about it. I'd love to hear your stories. And if you haven't touched AI before, I hope I've shown you that it's now so easy that absolutely it's worth you giving it a try and getting involved. Thank you for listening.